Right, thank you very much. So, all right. So, last time I introduced sort of the classical version of the BV-BFV picture for gauge theories, where you have certain supergeometric packages assigned to a bulk manifold and to a boundary manifold. And well, here's kind of a brief reminder of what they looked like. So there were kind of DG manifolds equipped with certain symplectic structures of appropriate degrees. And also kind of a Hamiltonian for the boundary homological vector field, and something that's almost a Hamiltonian for the bulk vector field. So, but being Hamiltonian is spoiled by a boundary term. So you could think of it as some sort of a DG Hamiltonian manifold, kind of relative to this DG Hamiltonian manifold. So it's some sort of a relative version. And the degrees are different, the degrees of symplectic forms and the Hamiltonian functions. Okay, so now also this is kind of designed to talk well to the kind of gluing and cutting of manifolds on which my field theory lives. So in particular, if I have some manifold that is cut into two parts by a closed n-1 dimensional submanifold, sigma, then, well, actually, the space of fields on the total n-dimensional manifold is a fiber product of the, so let's call M the whole thing, is a fiber product of the of this kind of packages for M1 and M2 over the phase space associated to the gluing interface. So more appropriately, this is a homotopy fiber product of these two objects. So, this sort of one can sort of pronounce all the correct words. So it is the fiber product of this sort of supergeometric packages over for M1 and M2 over this supergeometric package for the interface. Hey, so and one can also first of all one can also allow kind of extra boundaries here, so one can allow a picture like that, where you have some kind of M1. So for simplicity, I'm drawing cylinders, but of course they can be more complicated, some more complicated surfaces, and they could be glued over something. Let me call it sigma 2 now, and there could be some extra pieces of boundary. And then, well, you have again this fiber product picture, and also one can formulate sort of a classical field theory here as a functor in the spirit of Siegel's axioms, Siegel's axioms, where you would be assigning phase spaces to the to sigmas, this type of phase spaces with this BFV structure, and if you have a cobordism connecting to n-1 dimensional manifolds, then you have a canonical relation, or which is also called a Lagrangian correspondence between the two, which is given by what I denoted last time, L of M1, well, comma, its boundary. Let me not write that. That's
how is the function in the symplectic form on M related to those in 1 and 2?
right. Essentially, the function is just a sum of pullbacks of S here and S here, and similarly for the symplectic form. Here, no, there's plus sign. Yes. It's an integral over M splits as an integral over M1 plus integral over M2. Minus sign appears in the cobordism story for kind of boundaries. Here, this is a different construction. Here you have an orientation on, the sign is related to the orientation. You have orientation on M, it induces orientation on M1 and M2, and you're just summing omega on M1 and omega on M2. It's just that. Here, yes. Oh, you're asking about this part. Sorry. Here, this Lagrangian correspondence, yes, here there is a sign story. Yes, it's Lagrangian in phi sigma 1 with reversed symplectic structure, times phi sigma 2. Right, that's right. So it's sometimes people use this notation to indicate that this is not a map, it's a set theoretic correspondence. So kind of it's a subset in the product with the property that it's Lagrangian with respect to the symplectic structure. And then sort of the functoriality here is that if I have kind of a gluing of two cobordisms, then I have two such correspondences. And so this L is the following object. So you take solutions of Euler-Lagrange equations in M1 and restrict the fields to sigma 1 and sigma 2 and see what happens. So the pairs that come from a solution of Euler-Lagrange equation in the bulk, such pairs give me a submanifold in the product. So, so this is a relation, a canonical relation, or Lagrangian relation. So this is another one, and here I'm composing the relations. So L of the glued cobordism is the composition of relations here. Okay, so one more thing that I wanted to mention is that this picture has an extension for manifolds with corners, and on a classical level, it's quite straightforward. So these corner structures, so we got used to calling them BFKV, where K is a codimension of the corner. So it's sort of started from some extrapolation joke where, well, you have BV in the bulk, you have BFV on the boundary, so then in the corner you will just insert more Fs, right, as long as you're going higher in codimension. But I don't know, in our sort of community it's stuck, because you need to call this structure something. So, and the structure is like that given a codimension K stratum or codimension K corner, you're assigning, let's call this corner gamma of some manifold M with corners. So you're assigning to it kind of a similar package. Oops, it's some kind of corner phase space. Yes, exactly. Phi gamma, S gamma, Q gamma, and omega, which is exact. But sort of degrees here are K, 1, Q always has degree 1, and K minus 1. These are the ghost degrees, ghost numbers. This is a cohomological vector field. This is a graded symplectic form, and this is almost Hamiltonian for Q, again with almost Hamiltonianity spoiled by possible K plus 1 codimensional strata which bound gamma. So you have the relation that, well, similar to that one, so that the derivative of S gamma is the contraction of Q gamma with omega gamma plus the pullback of alpha for the boundary of gamma. So gamma itself could have boundary. So this sort of this picture becomes, so here it has only two tiers, sort of the bottom tier and the bulk tier, and you can sort of have more tiers in the structure for a manifold with corners. All right, so now kind of a class of examples where this promotion of a classical BV theory to manifolds with boundaries and even with corners goes completely straightforwardly is, well, a KSZ theory. So for them, everything is very nice. So the space of fields on M is, maps from the shifted tangent bundle of M to some target with appropriate DG Hamiltonian structure. Then if I have some stratum gamma, or some corner gamma of some codimension K, of any codimension K, then the corresponding corner phase space is, I write again that formula but replace M with gamma. So it's, for instance, if N is a graded vector space, those are differential forms on gamma. So differential forms on the stratum, on the corner with values in N, rather than differential forms in the bulk, on the bulk. And this corner action is actually the same, exact same formula as for the usual AKSZ action, but again, wherever you see M, you replace it with gamma. So you have the exact same integrand as before, but you integrate over gamma instead of M. And that means in particular that now it's kind of same integrand, but now you're selecting a differential form here of degree, which is dimension of gamma instead of dimension of M, which also implies that this will have different ghost number than in the bulk case. And similarly for omega gamma, it's also same logic. So in AKSZ theories, somehow these formulas for strata, for corners, they look exactly the same as bulk formulas. That's very specific to AKSZ theories. It's not true for, so you're integrating the same densities, but over strata instead of integrating over M. So this is not true for other gauge theories. So for instance, if you do electromagnetism or Young-Mills, you will obtain formulas that look different on corners and boundaries and corners than in the bulk. And I planned to give that example, but actually I have to cut it in the interest of time. But let me refer actually to the handwritten notes that will be uploaded on the conference website. So the formulas are there. So interestingly, they don't have this structure. So the formulas look different in different codimensions. So, okay. Now, another thing that I'm cutting it out, but I'm mentioning that it exists. There is a nice reformulation of BV-BFV structure in the language of variational bicomplex. So formulating everything in the language of kind of densities integrated over appropriate strata. So then these densities, they satisfy some nice relations, which are kind of the density version of these relations. So this is a nice story, but it's just another formalism. Let me skip it. So now, one thing that I wanted to remind to go forward, to go to quantization, is something that, I think is kind of very well known, but let me remind that there is the viewpoint of Atiyah and Siegel on quantum field theory as a functor. And I sort of already mentioned it here, but on the classical level. So Atiyah Siegel's axioms of QFT. So I will not try to be kind of detailed here. It will be on the sketch, and details can be complicated actually for geometric cobordism categories. So roughly speaking, the axioms say that an n-dimensional QFT is a functor of symmetric monoidal categories from, well, some appropriate source categories, some geometric cobordism categories. So n-dimensional cobordism between closed n-1 dimensional manifolds, and, well, they're allowed to be equipped with some geometric structure, and for different geometric structures you have different categories. So for instance, Riemannian metric, or I don't know, volume form, or flat connection, or any kind of local geometric structure. Or I don't know, orientation or spin structure also can go there. Okay, now, and this functor goes to some target category, and, well, okay, also different options here, but the traditional choice is vector spaces. Well, either vector spaces or Hilbert spaces. So, okay, let me sort of first say vector spaces. That was Atiyah's choice when he was thinking about the topological case. So let me denote this functor h comma z. So h will be its values on objects and z on morphisms. So objects are closed n-1 dimensional manifolds, n-1 dimensional manifold sigma, and such a manifold is mapped to an appropriate vector space, the space of states. So a morphism is a n-manifold with boundary, and I split the boundary into incoming and outgoing. So from sigma in to sigma out, or I can also call it a cobordism. So, and such a morphism is mapped to some linear map from H, from the space of states for the in boundary to the space of states for the out boundary. Now, functoriality here, as well, the word funct says that composition goes to composition. So, and composition on the left is the gluing of cobordisms. So, like on the other side. So I have a cobordism from sigma 1 to sigma 2, and the cobordisms from sigma 2 to sigma 3. And, well, they are glued into a cobordism from sigma 1 to sigma 3. So cobordism M. There are sort of a lot of subtleties here. So in the, if you are just looking at smooth manifolds, then maybe to talk about gluing, you need to quotient by diffeomorphisms relative to the boundary. Or, well, generally, it's actually better to talk about cutting manifolds rather than gluing. And then you should be maybe talking about functions of co-categories somehow instead of categories. But, well, let me not dwell on this. So this is, yeah. Cutting is much cleaner than gluing, but to talk about categories, you need to talk about gluing. So, okay. And a gluing of cobordisms goes into compositions, into a composition of corresponding linear maps. So the partition function for the big cobordism, Zm, so that should be, okay, that should be a map from H sigma 1 to H sigma 3. And this is just a composition of Zm1, which goes to H sigma 2, and Zm2. Okay, so that's the functoriality of gluing axiom. And also one has, so let me ignore this part, but the monoidal part is multiplicativity axiom. Multiplicativity says that a disjoint union goes to the tensor product at the level of objects or at the level of morphisms. And also that the empty object, so the empty n-1 dimensional manifold goes to the ground field. And okay, so that's one way of thinking about sort of Atiyah Siegel's picture, and another, and so original examples were, well, Atiyah was thinking about the situation where there's no geometry, so just smooth manifolds, and Siegel was thinking about two-dimensional Riemannian surfaces with boundaries, so there is conformal structure. Okay, so another kind of way of thinking here is to say that, well, for a manifold with boundary, I have some space of states attached to the boundary, and here I should actually, in this second version, maybe I should think that the space of states is a Hilbert space. So here I didn't really use it, but here I should use it, and I should say that, okay, I have for some manifold that is co-bounding sigma, I have a vector in the space of states for sigma, and then so vector in the boundary space of states. And then if I have a gluing of two manifolds along the common boundary, then what I should do, I should take a vector induced by M1 in the space of states for sigma, a vector induced by M2 in the space of states for sigma, and then take the Hilbert space in the product for them. So it's a pairing of Z of M1 and Z of M2 in the Hilbert space. Okay, in the Hilbert space. Okay, so this is a reminder of something that's kind of very very well known. Now let me go back to BV-BFV formalism, and I want to formulate for you what's the quantum counterpart of this picture. So the quantum counterpart is like that. So quantum BV-BFV. So there are kind of two stories. One is kind of the sort of axiomatization of the quantum BV-BFV theory, and the other question is how to obtain examples. And well, to obtain examples, you need quantization. So formulating quantum theory and formulating a recipe of quantization are very different questions. So, okay, the quantum BV-BFV formalism. So let's say I have some manifold with boundary. So it's some sort of a mimicking of Atiyah-Siegel's picture, but with some adaptations. So to the boundary, I want to assign, instead of this phase space, I will be assigning some chain complex, cochain complex, called, well, the space of states. But just now it's a chain complex. Sorry. Omega is the name for the differential, and so chain complex. And this is, well, its traditional name would be quantum BRST operator or quantum BFV operator. Let me call it that. And it's a differential, it should square to 0. And to the bulk, I assign two pieces of data. One is some kind of finite dimensional odd symplectic vector space. So with symplectic structure of degree -1, so odd symplectic vector space. And this will be something like the space of zero modes or space of residual fields. So they're actually, I'll talk a little bit more about it. So I'll call it the space of residual fields. So this is ultimately, okay, kind of space which abstracts the computation of the functional integral, the perturbative computation of the path integral. So you cannot obtain a number, you can obtain rather a function of these residual fields. And well, the most interesting part is the partition function, and that is, well, it's an, like in Siegel, it's an element in the space of states for the boundary, but it also has to be allowed to depend on these residual fields. So it's a half density on residual fields. So that's kind of the bulk data. And this object, the partition function, it's some sort of a mix between partition function because of that part and effective BV action because of that part. So it's an object that combines the properties of both. And it satisfies an equation which combines somehow the properties of both. And the equation, and here I'm kind of putting it as an axiom, that's the main structure equation. The equation is like that, that if I hit this z with certain differential, I get 0. And the differential is a combination of a differential on the boundary. So if I put sort of traditional normalization, there's some power of h bar going here. And then there's a kind of a bulk part that acts on the residual fields. And that's the, so if there were no this part, this would look like the BV quantum master equation. If there were no this part, it would look like asking that the kind of state induced on the boundary is gauge invariant, so it's killed by the BRST operator. And here we have some kind of combination of these two properties. Mm-hmm. Yeah, absolutely. Sorry? Oh, yes, so it would be sort of very nice to kill them completely. It's not, so in the framework of perturbative path integral, you sometimes don't know how to kill them completely and you just leave them hanging. So, and maybe you like to have as little of them as possible. But I absolutely agree, if you want to sort of have field theory, more in the traditional Atiyah-Siegel sense, where to a closed n-manifold you would have actually a number, then you would like to have no residual fields. But in the framework of perturbative path integral, that's oftentimes abstracted. It's sort of a separate question of whether you can integrate out the residual fields. Sometimes it can be done. So
Presumably there must be some equivalence between such data where you do some kind of reduction.
absolutely, you just anticipated my next comment. So that's absolutely correct. So so one actually has a certain choice here. One has a post set, a partially ordered set of, let me call it, I don't know, R. R is for realizations and residual simultaneously. So a poset of possible realizations of residual fields. Of the space of residual fields. So, and let me call them, well, V little r. So little r is kind of an element of this poset, so I have different realizations. If I can have sort of a bigger realization and a smaller realization. So let me use this sort of symbol for bigger and the smaller in a poset. So then I can split sort of the bigger realization into a smaller realization plus a complement as a symplectic, odd symplectic splitting, and do the push forward, BV push forward from the bigger realization to a smaller realization. So then the sort of smaller realization of my partition function should be the BV push forward of the bigger realization. So, and here, well, I imagine that there are different realizations of this space of residual fields. There is some kind of smallest realization, which I call zero modes. And sort of there is some sort of infinite dimensional realization, which is the original continuum fields. Or actually, continuum fields subject to a boundary condition. But there is some sort of infinite dimensional object which is bigger than everyone here. So and then there are arrows corresponding to, well, going from large object to smaller object. And you can sort of jump along those arrows by this rule. So, okay, so then here I should sort of say that there's this choice of realization in the game. All right. So, okay. So I wanted to have this type of data, and also in this setup, I would say that the gluing is given by sort of a formula similar to this one. The idea is that, well, you want the partition function of M of kind of a glued manifold, M1 glued with M2 over some sigma. Okay, so in the first approximation, you take the partition function for M1 and partition function for M2. So, and you pair them in the space of states here, in the space of states for the interface. But then you need to deal with the fact that, okay, maybe let's consider the sort of smallest possible choice of residual fields. So then the smallest possible choice of residual fields for the glued manifold is usually smaller than kind of the Cartesian product of residual fields on M1 and M2. So you need to somehow, so this Cartesian product gives you a non-minimal object in this poset, so you need to still jump to this minimal object. So I need to do an additional push forward to this smallest residual fields, smallest residual fields on M from the Cartesian product of residual fields on M1 and residual fields on M2. So this becomes more concrete in examples where kind of the smallest model for residual fields corresponds to some well, cohomology actually, or cohomology relative to one of the boundaries. So, okay, so this is a push forward for residual fields. Now, okay, so these are the axioms, and how does one construct examples? So, okay, So I want to give sort of a heuristic idea of quantization and then a class of examples. So this heuristic idea can be made precise in classes of examples, and I'll describe one class. Okay. So okay, so the idea of quantization. So if I'm given a classical BV-BFV theory, how to construct a quantum one from it? So I'm given a classical BV-BFV theory, and I want to construct out of it somehow a quantum one, quantum BV-BFV. So okay, so I need to somehow quantize the boundary data and quantize the bulk data. So for the boundary, we do the following. So we are given our BFV phase space for the boundary, so which is, that's sort of supergeometric package. So the graded manifold, graded phase space with its BFV action, the cohomological vector field, and an exact symplectic form. So okay, so the idea is essentially to use a geometric quantization here, or even a particularly simple form of geometric quantization. So let's choose. So for geometric quantization, you need a polarization of the symplectic space, and here let's choose a particularly nice one. So some fibrating Lagrangian polarization. So of fibration by Lagrangian submanifolds of phi sigma, which is given by, well, some map from phi sigma to some base manifold, such that, well, fibers of this map are Lagrangian. So, so this is my picture for phi sigma, this is B sigma. So the preimage of a point here, of a point, I don't know, B, would be some kind of Lagrangian here. So, okay, I want an extra condition that this polarization is compatible with this one form alpha in a particular way. So an extra condition that alpha restricted to these fibers is 0. Is 0. So this leads to a very simple case of geometric quantization. So so we construct the space of states as, well, okay, as a geometric quantization of the symplectic manifold with trivial pre-quantum line bundle. So for the pre-quantum line bundle, I just take the trivial line bundle with connection given by the one form alpha. And for polarization, I, well, take this polarization. So, okay, geometric quantization, so this, the space of polarized sections. So in this polarized section of this bundle, so in this case, under this assumption, this is just the same as functions, or, well, depending on your setup for geometric quantization, half densities of on the base. I'll be a bit sloppy between half densities versus functions. It's more appropriate to talk about half densities. So now okay, so this gives us this space, which is okay. It's actually okay. It will be half densities on some graded manifold, so it's a graded vector space. And for omega, so I need to construct a differential here. So let me kind of schematically say that it's a geometric quantization of S sigma of the BFV action. So here, being geometrically quantizable is kind of, in a strong sense, is very restrictive. Usually, a sigma is not quantizable in the sense of geometric quantization, and so doesn't preserve the polarization. And then there is some sort of ordering ambiguity in the quantization, and you need to resolve it somehow. In particular, you want omega 2 squared to 0. So that's one of the requirements that you want to have. But this is a starting point. So this should be a geometric quantization of some geometric quantization, so with some ordering of S sigma. So in concrete example that I will give, there's actually a particular explicit construction for omega such that all the properties that we want, namely that omega squares to 0 and that this is true, the quantum master equation is satisfied. Yeah, I didn't give a name for this equation, so we got used to calling this unimaginatively modified quantum master equation. So I don't know, that's kind of our name for it, modified quantum master equation. So, okay. Now, okay, so that's the quantization of the boundary. What about the bulk? So bulk quantization. So I have the space of bulk fields from my classical BV-BFV data. And there is a surjective submersion to the phase space for the boundary, and so that was called pi. And there's also my fibration P that is my sort of geometric quantization datum. Such that the fibers of P give me the Lagrangian polarization. So okay, then if I fix some, maybe I can put declaration sigma here. So if I fix some point here, little b, then, well, the fiber over here would be some kind of Lagrangian, P inverse of b. And if I look at the preimage here, then, well, what I see is fields such that their boundary values belong to your given Lagrangian. So B gives me a boundary condition for fields, for bulk fields. So let me call this kind of pre-image of this Lagrangian. Let me call it phi B. So fields subject to the boundary condition B. The boundary condition B. So what I have here is a setup where I have a family of boundary conditions that I can impose. For instance, I don't know, in quantizing classical mechanics on an interval, I can fix, I don't know, coordinate, like, I don't know, a position of the system at the initial time and position at the final time, or position at the initial time and momentum at the final time, for instance. So that so I'm fixing a Lagrangian in the in-phase space, a Lagrangian in the out-phase space. Then I can look at sort of kind of histories of travels of positions and momenta, such that, well, let's say initial position is fixed, final position is fixed. That's an example of this situation. Okay, so now what about the partition function? So in zeroth approximation, the partition function is something depending on B, on this boundary condition, and it is just the path integral with boundary condition, or functional integral with boundary condition. So I should be integrating the exponential of the action. So, okay, let me say that I would like to write my space of fields as a product of these possible boundary conditions times y. So, and y are somehow fields with, let's say, zero boundary condition. Let's say that I'm in linear setup, so that these are vectors. vector spaces, so there's a 0 here. So these are fields in the bulk with a boundary condition corresponding to 0 here. So I want to have a splitting of this kind. So, and I want to have a Lagrangian in here. And this is the gauge fixing Lagrangian. So that Lagrangians appearing in different, Lagrangians with respect to different symplectic structures of different degrees. And so there are Lagrangians that describe boundary conditions. This is a gauge fixing Lagrangian. Gauge fixing Lagrangian. So here I want to integrate over that Lagrangian in Y. Okay. Yes, please.
So you're not going to explain what the residual fields are.
I will in a second. That's why zeroth approximation. You see, there's 0 here.
Right, but I mean, Z should be in the space.
Yes, absolutely. I'm coming there.
We're going to define Z and then where it lives.
Well, so far in zeroth approximation, there's no second factor. In zeroth approximation, in zeroth approximation, this is a point. So yes. So and it is then so I fix an element here, and I'm integrating over an element in Y over a Lagrangian. So it's a BV integral over a Lagrangian inside Y. So that's the idea. So I'm kind of writing it schematically. So the way that we can do something with functional integrals is, well, if they look like perturbed Gaussian integrals. And then we sort of want to calculate them by Feynman diagrams. So, and then usually, oftentimes this is abstracted. Sorry, question? So this is not a splitting with respect to the symplectic form. This is there is a weakly non-degenerate symplectic form here, which restricts to a non-degenerate symplectic form here. Here it doesn't induce anything interesting. Yes, it is actually. It is an artifact of. Yes.
But you assume that there is a symplectic form on Y.
So it is induced by it is induced from symplectic form on F. So essentially, Y is let's say that there's a 0 in this space. So Y is pi inverse P inverse of 0. That's the idea. So it's certain fiber here. So I just restrict omega to this fiber. So that is the idea. Right. So it is like, for instance, I don't know. No. Okay. So it is fields with a certain particular boundary condition imposed. So. This point here is kind of analytically a little bit tricky to explain. So, because one map here is sort of well-defined, and the other map you need to construct somehow, and usually you construct it as a limit of some ways to extend boundary fields into the bulk. So there is some kind of there is some subtlety here in writing it this way. So I'm cutting corners. So, okay, but I want to imagine that my space of fields, I can think of it as boundary condition and sort of a field with trivial boundary condition. And on fields with trivial boundary condition, I have a symplectic structure. Here, actually, for each little b, I have a symplectic structure on this fiber, induced from omega on the omega m on the whole thing. Right? And this is, again, this is an artifact of infinite dimensional setting that, well, you can have this kind of a weakly non-degenerate symplectic structure on the entire FM and symplectic structures induced on fibers of this fibration over B. Okay, so Now, the problem with this integral is that it's usually abstracted as a perturbed Gaussian integral, is abstracted by zero modes, is abstracted usually abstracted as a perturbed Gaussian integral, perturbed Gaussian integral by zero modes. So usually you cannot actually choose a Lagrangian here such that the quadratic part of S restricted to that Lagrangian is non-degenerate. Usually there is some finite dimensional degeneracy and you want to kill it somehow. And the way to kill it is, what results in these residual fields. So first approximation. So first approximation is that, I want to split Y as some kind of finite dimensional part, V, the residual fields, and its complement. And I want this to be an splitting of odd symplectic manifolds. Yes, of odd symplectic, well, let's say vector spaces if we're in the linear setting. So, and these are my residual fields. Or kind of their smallest possible choice such that I can calculate the integral over Y double prime is what I call zero modes. So, okay, and then my partition function will be a function of B and an element here. Let me call it phi residual. And it is an integral now over a Lagrangian in Y double prime. And I'm integrating the exponential of S of B, and then phi itself is split into phi residual, and I don't know what to call it, phi fluctuation, let's say phi fluctuation. And I'm integrating over phi fluctuation. So, okay, so the result depends on this little b and little phi, and this gives me, well, up to not thinking too much about half densities versus functions, this gives me a half density on this base of this fibration P cross V, which is well, an element of my space of states, tensor half densities of residual fields. So, okay, so that is kind of the heuristic construction, and this is kind of the idea why we need to split off the residual fields and why we need to sort of have this extra bit in the axioms. So, and now, now an example. So, yes, please. Yes. Right. So in the case of scalar field, I would split. Well, let me actually. I don't want non-compact manifolds. Let me take a scalar field on a compact manifold. But yeah, there would be kind of a zero mode here, which is let's say it's a massless scalar field. Actually, the situation depends on whether it's massless or massive. For a massless scalar field, yes, there is a zero mode, which is constant, and I would split the constants and construct sort of half density on those constants. Absolutely. Right. No, I'm not saying. So, so here we're kind of we have examples where there could be some other things rather than constants to split out. But yes, so the idea of I don't know, Wilson's effective action or effective action on constant fields, for sure, we were not the first to come up with it. So here there's kind of a particular class of examples, I would say, and also a discussion of how it is compatible with gluing, which is, I guess, not in the writings of founding fathers. So I don't know if I answered your question, but yeah, I agree that in the scalar field I would also split out constants. Sure.
construction of Z with some choices of Lagrangians.
Yes, absolutely.
Construction of
Yes.
Z
Oh,
choices, but then in the end you want actually to have
okay, so yes, so you're asking a good question. So first of all, there was a choice of this polarization, and here, of course, the axioms should be sort of adjusted to conform with what we actually obtained. So boundaries actually should be decorated with this choice of polarization. So that should be a part of decoration of boundary. So, but then somehow different choices, so different choices give you a different model for the space of states, and but there should be some kind of quasi-isomorphisms between corresponding complexes when you change the polarization. That's one part of the story. The second part of the story, you asked about choice of a Lagrangian, and that's absolutely also an absolutely right question. And actually, the thing that I should have said is that Z is defined, so is supposed to be a cocycle for this differential, but it's defined up to a coboundary of the separator.
But you claim that no matter how you make your choices, the equation is satisfied.
Yes. So, okay, this is sort of, there is some heuristics why they should be satisfied, but this is kind of manipulations with path integrals. And in explicit examples, you kind of present this data, and then you need to check the equations.
Miraculously flop.
Yes. So as usual, sort of path integrals give you a guiding, give you a working conjecture, what you should expect. And then you need to prove it somehow separately. Maybe actually this is a reasonable place to make a small break, like 5-minute break, and we proceed with examples. So I want to actually go to Feynman diagrams. I should just say that, well, we are kind of starting early today, and I had acquaintance, Russian physicist Dmitry Diakonov, and he once told that he used to calculate Feynman diagrams before breakfast. So, okay, so let's make a 5-minute break. So until 10:03, right? So that's it.
One quick question, maybe easy one. If you don't have boundaries, then your f is directly your y.
Exactly. Yes, absolutely. Mm-hmm.
So you don't you skip
Then-
like this part and you go directly to
Yes, that is the story of effective action, actually, if you don't have boundary.
this.
Yes, exactly. And then you still, yes, you still have to split it.
Yes.
And then you obtaining an effective action on V.
Okay.
Yeah, so this becomes the story of effective action.
Yes. Okay.
Methodological question. Why you skip y prime and straight went to y double?
So I like when I split things into.
Something.
It's a mixture of conventions. So I like splitting fields into slow and fast and calling them prime and double prime.
So v used to be y prime.
Yes, but notice one very nice thing that V is a deformation retract of Y. The letter V is a deformation retract of letter Y. You are contracting the bit. So, and that works well with the examples. It should be a deformation retract. All right. Come again?
There was this bell to call people, but I don't see it anymore.
Oh. All right. Ah, bell. Okay, yes. Right. Uh-huh.
What can go wrong in this picture? For instance, you say that you have to quantize omega sequence such that the square is zero.
Yes.
In some example, did you find some obstruction?
Yes. Well, actually, the sort of example that was even before the whole machinery was produced is 1D Chern-Simons. Actually, there, omega is the cubic Dirac operator, and the cubic Dirac operator. So, and it squares actually not to zero, but to a central element proportional to the quadratic Casimir in a joint representation. So for some class of sort of input Lie algebras it vanishes, but generally it doesn't. So there is some.
So can you adjust the picture?
No, but it somehow it doesn't mess things up too much because somehow adjoint of this operator still squares to zero. So the quantum-master equation is satisfied. It's actually the first example where it was observed. So that's in. Yeah. So yeah, but there you have these two operators on the two endpoints of interval, which individually don't square to zero, and that's your sort of quantum BFV operator. So there is some kind of mild version of gauge anomaly there. Yeah. So that's the one example I know. But I'm sure that things can go much more wildly wrong. But yeah, I just don't know. Yeah, maybe if you consider, I don't know, like Poisson's sigma model without unimodularity condition, or maybe something like that. Is it a good time to start? Oh, right, all right, okay. So let us continue. So, okay, my goal is to talk about some kind of a subclass of AKSZ theories, some perturbations of BF theory. So, but let me first explain the thing we can perturb around. So the abelian BF theory in this context. It's a nice exercise to construct it. So the reference here is to it, and the perturbed version, where you do have Feynman diagrams, is our paper with Alberto Catania and Nikolai Reshetikhin called perturbative blah, 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 perturbative gauge theories on manifolds with boundary. That was it. So, okay. So we think of a manifold with boundary, so a cobordism, which has in boundary and out boundary. So, so for in boundary, I want to, okay. Okay, so the space of bulk fields is the space of differential forms on M. Actually, two copies of it, corresponding to the fields A and B. So N is the dimension. So I have a field A here and B here. I'm sorry that my notation for field B is the same letter as sort of base of that fibration, so let's try not to confuse them. So the phase space, okay, it's made up of two parts, the in-phase space and the out-phase space. So, well, it's phi out and also phi in. I can write plus because kind of those are linear spaces. So, okay, and there's a projection by restricting to the boundary. And actually, phi out is just my A fields on the out boundary and B fields on the out boundary. Let me just write it like that. And here, omega stands for differential forms. And I also have A fields on the in boundary and B fields on the in boundary. Okay. All right. So, and then I want to choose this kind of fibration. I want to choose this fibration P. So, okay, I want to select. What is M? Oh, that's the dimension of M. Little n is the dimension of M. So, okay, the fibration will be like that. It selects the value of the A field at the out boundary. So, well, so I remember the A field at the out boundary, and the values of the fields on the boundary. For some reason, we got used to denoting them A and B with double leg, but that just means the boundary fields, the restrictions to the boundary. So, and so I remember the A field, so this is, I don't know, A and B on the out boundary, so I only remember A, and I forget B. So B is in the fiber of my Lagrangian fibration. And on the in boundary, I do the opposite. I remember the B, and I forget the A.
B is 1/4 from the out and 1/4 from the in.
Come again?
B is 1/4 from the out plus 1/4 from the in.
Yes, that's right. That's right. Yeah, absolutely right. This is just one possible ways to do things here, but let me do it this way. So it's like in when constructing, I don't know, path integral of quantum mechanics. For quantum mechanics, you can, I don't know, fix the in coordinate and out coordinate or in coordinate out momentum. Here I'm doing like out coordinate if I call A coordinate and in momentum, something like that, if I call B the momentum. So I remember the out out A field and the in B field. So I want to fix them. And so I don't care about the value of the out B field and the in A field. So that's kind of in the fiber of P. So then, if I have fixed the A at the out boundary and B at the in boundary, then I'm looking at fields with those, where A field has this prescribed restriction on the out boundary and whatever restriction here, and the B field which has this particular restriction at the in boundary and whatever restriction here. So then I have a splitting like this one, where Y is, okay, so Y is the fiber of P composed with pi, and it is differential forms, so for the A component, for the A fields, differential forms on M which vanish at the out boundary. So let me write it like relative forms. Relative means vanishing at the out boundary. And also I have B forms which are relative to the in boundary, so they vanish on the in boundary. So that's the description of this fiber of P composed with pi. So now V, so I want to construct this splitting of Y into V plus some complement. So by the way, the symplectic structure on Y is just the integral of a product of differential forms. So V, I want it to be, well, actually just the cohomology of y with respect to the RAM operator. Or more explicitly, it is a cohomology of M relative to the out boundary with its shift. So that's kind of the A residual field, or A zero mode, because actually this is the smallest possible residual field in this model. And another copy relative to the in boundary, and that's kind of the residual B field. And I will be denoting them little a and little b elements here. So the residual A field, residual B field. And there's a symplectic structure here which just comes from Poincaré-Lefschetz duality. So I represent those both by differential forms, integrate the products.
I'm sorry, are you saying that the RAM differential preserves the condition of vanishing?
Yes. Yes, it does. Absolutely. It is a complex, right? So, I mean, it's a subcomplex inside differential forms. Vanishing, I mean that the pullback vanishes. Pullback by the inclusion of the boundary vanishes.
Can't you have a function which vanishes, function a segment which vanishes at the ends, but its differential is not
how to say? So its differential will be a one form. Pullback of a one form to the end is zero, because pullback of a one form to a point is zero. Right? So vanishing, I mean, by vanishing, I mean that the pullback vanishes. I don't say anything about normal directions. Mm-hmm. Yes, please?
If we think of A as a connection, then I can't imagine that they form a vector space, because we can't sum to...
This is abelian theory. So here, my fields are differential forms. I'm not thinking about, so I don't have to think about any global phenomena like what you're thinking about because, well, okay, it's an abelian theory. Gauge group is R.
But still, it must be gauge invariant, because you can still do a gauge transformation, but sum of two connections between gauge.
I'm not thinking about them as connections here. They are just differential forms. And gauge transformations are by shifting by an exact form.
So you didn't explain any of your classical data. So only to presume pairs couples the two parts in fields.
What?
The definition of omega S and P you explain, right?
The definition of omega, so that's the integral of a product. What is S? Sorry, yes, I thought that I wrote this theory before, but yeah, this is S. And S boundary is the integral over the boundary of BDA. Mm-hmm. Mm-hmm. All right. So, okay. Yes, please. Yes, for both, but the integration is over a space of different dimension, right? That's a property of an AKSD theory.
Oh, so these are not the same things.
Okay, these are fields restricted to the boundary. Yes, yes, right. Uh-huh. All right. Now, okay, so this V is actually a cohomology of this big complex. I could say also deformation retract of this big complex. Okay, so what did I want to say here? Yes, so I want to describe the gauge fixing. So, okay, to describe the gauge fixing. So, let me choose some basis in this cohomology relative to the out boundary, and choose representatives for these classes in differential forms. So choose representatives chi A, of cohomology classes, of some basis of cohomology classes in, cohomology relative to the out boundary. Okay, so and then I have the dual basis for the cohomology relative to the in-boundary, and I can choose sort of the dual representatives such that the in the product is the Kronecker symbol. So dual representatives of classes in cohomology relative to the in-boundary. By Poincaré-Lefschetz duality, right? So yes, so this is dual to this. Yes. So these are the integration of differential forms gives integration of a product of differential forms gives a non-degenerate in the product here. It's a theorem. It's called Poincaré-Lefschetz duality.
One boundary is empty.
Yes. Then you have h of m comma sigma. Let's say in is non-empty. Then there is a kind of right. Then there's a pairing like that, which is non-degenerate. Okay, so this is kind of an input from, I don't know, algebraic topology. So let me just take it, but yeah, it is true. So okay, so I have some collection of representatives of classes relative to the out boundary, representatives of classes, dual collection of representatives of classes in the in boundary, relative to the in boundary. So then, okay, so then one can construct in many ways, so there are sort of various constructions, how you can construct a chain homotopy, contracting this, okay, this complex, oops, contracting this complex to its cohomology. So one can choose a chain contraction. Let me call it K. So it will be a contraction or chain homotopy. So it will be an operator, some kind of integral operator, linear operator, dropping the degree of the form by 1. So it will be given by an integral kernel. Let me call this kernel eta. And this is kind of a notation that will be our propagator in a moment. So we'll call it propagator. So it is an n-1 form on the configuration space of 2 points on M with certain properties such that, some boundary conditions that eta of xy is 0 if x is in the out boundary or y is in the in boundary. So that's one condition. Second condition is that d eta is, eta is almost closed, but d eta is sum of chi a tensor chi a. And finally, a condition that if I take eta and integrate sort of the first, I fix y some point in M, and I integrate x in a little sphere around y, a little n-1 dimensional sphere of tiny radius epsilon, and I take the limit of this epsilon to 0. Then in the limit, I will get 1. So yeah, this is sort of a class of chain contractions that are given by such particularly nice integral kernels. There are also chain contractions that are given by more singular integral kernels. And there's a way to construct them, for instance, by on a closed manifold, you can take sort of the Hodge construction. You can take d star divided by the Laplacian. So my propagator is a differential form depending on 2 points in M. So I fix 1 point someplace and I integrate over the other point in a little sphere. This integral should be equal to 1 in the limit when sphere becomes very, very small. It's an equality for a limit, yes, when epsilon goes to 0, the radius of the sphere. Form is almost closed, yes. There's this cohomology that obstructs its closedness. Yeah, so one can, for instance, look at this operator and construct its integral kernel. It will have these properties. So one needs to sort of adapt it for the presence of boundary. For instance, one can do some kind of image charge method. So there are constructions. There are different constructions for such propagators. For instance, starting from the input of, like from Hodge-Derham theory, that's one of the possible constructions. Okay, so now I can kind of start describing the result for this abelian theory. So, okay, so the space of states.
This K cannot be described topology.
No, no, I mean, it's always some kind of integral operator.
And there are some, it really depends on some continuous parameters.
I'm not sure what you mean by it.
Maybe it depends on like choose a vector.
So, no, so there's a huge sort of huge space of possible Ks. So usually we just choose one possible K described by some eta. So this is a choice of gauge fixing for us. So then one can study dependence on what happens if you have a family of propagators and if you change it and then you prove that sort of the result is up to appropriate equivalence is invariant. So, okay, let me describe the answer of quantization here. So the space of states, or quantization of the boundary data. So the boundary data for abelian BF theory was, well, the phase space that was, well, this one. So, and the kind of BFV action on it, that was the integral over the boundary of BdA, or I guess I'm calling it B and A with double leg to emphasize that they're on the boundary. So the quantization will be kind of so the space of states, which is a product of a space of states for the out boundary and space of states for the in boundary, where here, well, sort of ignoring the distinction between half densities and functions, let me just write here functions of the out A field and functions of the in B field. More appropriately, I should be talking about half densities, but let me drop this. So what kind of functions? So I should be thinking of functions of the following type. Sum over k non-negative, the integral over configurations of k points on sigma out. I take the product of A out. Okay, so let me write it like that. Product of A out, which is a differential form on sigma out, and then I have k different projections from the configuration space of k points to sigma out by selecting the position of kth point. Let me take the pullback by the first projection, and then, and so on, pullback by the last projection. So, and then I want to multiply it by some differential form on the configuration space of k points. So this is kind of my boundary field, and this is something that I select, and this is a wave function. It's sort of a k-point wave function. So this collection of wave functions gives me a particular state. If I prescribe this collection of functions on configuration spaces, I prescribe a state. So, okay, so k-point wave function. All right. So okay. So just some smooth function on the configuration space.
Sorry, what just happened? So what is this thing you're explaining?
I am explaining what kind of so this looks like functions on some huge space of fields on the out boundaries on this functions on the space of differential forms. That looks very big. So I'm giving a more sort of hands-on model for functions that I'm interested in.
It's a span of functions like this?
Yeah. Yes. Just functions like this.
Where
Psi k is some smooth function on the configuration space. That's still a lot of functions, but I would say more handleable, right? So it's not as scary, I think. I think it's slightly less scary. So okay.
the sum can be infinite over k?
Yes, it can be infinite. Yes. No, but in the examples you're constructing kind of some state which is described by particular psi k's, right? So yes. Now the differential, this BFV differential, is some operator on this space which splits into omega out acting here. So it splits as omega tensor identity plus identity tensor omega in. And omega out is the integral of d a out, the derivative in a out. And omega in similarly, but for b and integration over the in boundary. Okay, so and then for the let's see, where can I erase? Yes. Okay. So yes. So for the quantization in the bulk, so I follow the strategy that I just erased. So, but yeah, I was having trouble with board space. So okay. So bulk quantization. So the partition function now will depend on the A out field, B in field, and then also the zero modes A and B, which are together give me a point in V in the space of zero modes. So A is a cohomology class relative to the out boundary, B is a cohomology class relative to the in boundary. So cohomologies of bulk, so they're bulk zero modes. And this is a differential form on the out boundary, this is a differential form on the in boundary. So what I'm trying to, sort of the heuristic expression is that it is an integral over a Lagrangian in y double prime, where y double prime is somehow the complement of right. So here, okay. Let me maybe say that, well, okay, maybe better said in canonical quantization. So you have, let's say, some splitting of.
The functions kind of quadratic.
Sorry.
Okay.
Right. So here it is actually canonical quantization. So our omega was b dA, and then b on the out boundary became the differential operator, and dA is still dA. And on the in boundary, the opposite happened. So all right. Now what I want to do is to integrate over a Lagrangian in the complement of residual fields, in the complement of cohomology inside this pairs of differential forms with vanishing conditions, appropriate vanishing conditions on the boundaries. And I want to integrate, okay, exponential of I over h, my action, of field A, which I represent as, well, the A out somehow extended into the bulk. And here actually I want to do this limit of sort of extensions which are supported very close to the out boundary in the limit, where sort of it becomes a discontinuous extension. So there is some limiting procedure here. So this twiddle stays for this extension, plus the kind of element of the cohomology take the representative in the in omega dot, for instance, in differential forms, for instance, by harmonic forms.
Sorry, what is y double prime?
Yes, y double prime is okay. It's the, so actually I fix. Yes, so it's everything that integrates to zero against chi's. Yeah, everything that integrates to zero against chi's. So that's y double prime.
L is just one half.
L is 1/2 of it, and actually it's 1/2 that's given by the image of K, of the separator K. So in 1/2, and in the other half, it's the image of the K sort of transpose. So L is constructed out of K.
Ah, I see. So Lagrange is non-trivial.
It's non-trivial. Yes. It's constructed out of K, exactly. Yes, image of K plus image of K, well, transpose. Yes, so, all right. So, yes, so I have sort of my field, I'm splitting it as, well, it's actually, maybe I shouldn't have erased it. So, sort of the representative of the boundary field, the residual field, and somehow the fluctuation. Maybe let me call the fluctuation alpha. And similarly for the B field. So it's a B field extended into the bulk, then the residual field and the fluctuation. And I need to integrate over these fluctuation fields. So that's sort of the heuristic expression, and then one sort of looks at this exponential here, and one recognizes that it's the kind of two terms which are boundary integrals. Let me write it like that, and sort of a bulk integral beta d alpha. So this looks like this is kind of the Gaussian integral. So these are my dynamical fields that I'm integrating over alpha and beta. And here they enter linearly. So you recognize this as a Gaussian integral. So infinite dimensional Gaussian integral. So, and then sort of inspired by this expression, you write, it's okay, it's an extension of this differential form on the out boundary into the bulk by sort of which is supported in a small tubular neighborhood of the boundary. Yes, yeah, exactly. And then you need to take a limit when this sort of neighborhood shrinks. So this is actually there's a limiting procedure hidden in that symbol. That's the my chosen representatives of cohomology classes inside differential forms. Yes, I is sort of this inclusion of cohomology, and chi was for my particular basis. I chose some basis. I'm sorry for my notations, but yes. Alpha is this fluctuations. So these are the elements of y double prime, which I'm integrating over, well, but I'm integrating over Lagrangian there. All right. So then, kind of inspired by this infinite dimensional Gaussian integral, we write down some expression, which can be called the computation of this integral, or if you don't believe in functional integral, will be kind of just the definition, for which you will then later be checking the properties, the desired properties. So there will be some kind of prefactor, which I'll say in a second what it is, which we could say a constant times the following thing. So the integral of the out boundary BA, so B is this cohomology class, A is this differential form on the boundary. Let me not write out. Plus integral over the in boundary A B, sorry, capital B, A. So it's again a pairing between the boundary field and a relative cohomology class. And then there is sort of the term where the two boundaries talk to one another. So there's, let me write it like B of x, A of y, and schematically eta of xy. So this is the propagator that connects the two boundary points. That's the exponent. This thing is the torsion, the Ray-Singer torsion relative to the boundary. So it's an element of the determinant line of cohomology, which by happy coincidences is also the space of half densities of my residual fields. These are actually constant half densities of residual fields. So this is the formula. So how to so this part of understanding understanding the torsion as appearing from such Gaussian integrals, this was somehow one of the kind of birth points of topological field theory. This was a paper of Albert Schwarz, also from 78-ish, which was called the partition function of a degenerate quadratic functional. He sort of pre-invented BV there before BV, or invented it in a special case. So kind of a picture that comes with the terms in the exponent here is that, well, I have the A field on the out boundary, and here I have sort of this B0 mode talking to it. I have this term where I have the B field on the in boundary and a zero mode talking to it, A0 mode talking to it, and I have a term where the B at the in boundary talks to the A on the out boundary by a propagator. Okay, so and then one can sort of go on and check that all the properties, all the axioms of.
Before checking the property, it should be in densities of tensor H, right? And how is it?
Right.
How is this exponential in H?
Well, this exponential is in the tensor product itself, so it's.
Last two, this is I see, but the last one, how is it in tensor product?
Right, so it's in H.
Some completed tensor.
Oh, of course, yes, completed, sure. Sorry, I just completely ignore all functional analysis. So completed, sure. Yes, of course. So yeah, I'm not going to go to check the properties, the axioms, but they do hold here, and this is not a complicated computation. One interesting part here, for instance, it's a nice check like that the quantum mass equation, this modified quantum mass equation holds here. This is not hard. So a curious check is the gluing formula. The gluing formula works, but it corresponds to if you do this gluing as described in the right side of the gluing formula for two such partition functions, for two manifolds M1 and M2, then you obtain the partition function of this type for the glued manifold, but with a very special choice of eta, with a special choice of chain homotopy that is somehow glued out of chain homotopies for M1 and for M2 by a curious sort of gluing formula. So let me just emphasize one part of this gluing formula. So there is some glued chain homotopy with its sort of glued kernel, and well, it depends on 2 points on the glued manifold M, and it sort of depends on where X and Y fall. For instance, if X is in M1 and Y is in M2, then what I should do to obtain this glued chain homotopy, I should take eta of xz for the manifold M1, where z is some point on the interface. And I should take this propagator for M2 between Z and Y. So we usually put some arrows here because these are kind of not symmetric. And integrate over Z, integrate over this point Z. So this integral gives you this chain homotopy. And there are some other rules, like depending on whether, like if both points are in M1, you just take eta 1. If both points are in eta 2, you just take M2. You just take eta 2. If they are in different halves, but kind of in the opposite way, then this propagator is 0. So this gluing formula corresponds to calculating the partition function on the glued manifold in a very special gauge. And here we sort of have a explicit construction of this gauge, or explicit construction of a gluing for chain homotopies.
So, sorry, before also, you should have probably mentioned that, so the Z, then you, this lives in some complex. You're saying that up to maybe, up to Kabam, it doesn't depend on some choices, right?
That's correct, that's correct. It actually, it is true that if I change the choices, then it changes by this, well, delta V, whatever the normalizations are, omega for the boundary of blah. So if I change the choices, I change the result by a term of this type.
Particularly if you change the propagator.
Absolutely, yes, absolutely. And you can, moreover, you can explicitly express the blah in terms of the change of propagator.
So, okay, so the question is, so I see that if you kind of pass the homology in the complexes, then you will have kind of gluing, like in a very
On the nose, yeah.
on the nose, but maybe if you don't do that, then you should have done some kind of high compatibilities, whether it's like the position of 3 or something like that, right? It's being considered.
No, I think we were just happy with that property.
No, I think
Uh-huh.
it's just that there should be some lax structure.
Right. So you're interested in some derived structures. So there could be some derived structures here, for sure. No, I agree. So I guess at least I'm not ready to comment on them. So I cannot vouch for my co-authors. They might have thought about it, but No, what I was trying to say is that if I calculate this Z for some very particular choice for M1, for particular choice of propagator eta 1, and I sort of construct this gluing as in the right-hand side there by pairing in the space of states, let me just denote it like that, with Z for M2 with some propagator eta 2 that corresponds to calculating Z on M with some very special propagator, which is constructed out of eta 1 and eta 2. That's what I was trying to say. Okay, so now to the sort of perturbed version. Let me see what I can erase. Okay, so let's see. Maybe that one. I don't know. Okay. No. All right. Let's erase that one. Okay, so the class of examples into which you can perturb that example over there is, well, BF-like AKSZ theories. So so here the space of fields is the space of differential forms on your manifold M, tensored with some kind of coefficient space, which is a graded vector space. So kind of that's a half of the space of fields, and that corresponds to my A fields. So I have now A fields with coefficients somewhere. And so this is a graded vector space. And I also have a B fields, which are also with coefficients in V star. So let's say V is some finite dimensional graded vector space. So this is the B field. And then, okay, in terms of a KSZ construction, the target is V plus V dual with a shift. Oh, sorry, I should have put a shift here, and -1. So this is the KZ target. And I want to reserve some function on this target which satisfies the equation theta with theta Poisson bracket is 0 with respect to the symplectic structure here. So, and then, let me not write subscript n here. So then the action is the integral of b dA plus theta of AB, integral over m. And for sort of boundaries, for instance, the same formula, but the integral over the boundary. So, okay, then, okay, I'm thinking again about some manifold with boundary. And I fix A at the out boundary, so that will be my choice of polarization, and B at the in boundary. So the space of states is actually the same as in the abelian case, although now fields A and B, they are differential forms valued in some, with coefficients in some graded vector space. So for instance, H out is, well, functions of A out, and actually functions of this type that did I raise it? I'm sorry, I think I raised it. No, I didn't here, of this type. So prescribed by some collection of wave functions. So omega is something complicated, which I will comment on in a moment. Omega is much more non-trivial than what was written here. It's actually given by configuration space integrals. Now, partition function. Okay, so the space of residual fields is also as in the abelian case. So the partition function of A out, B in, little a and little b. So the fields on the boundary and the residual fields are the same as in the abelian case. And this will be the same prefactor as before, the torsion prefactor, tau of m sigma out, times, and then, well, the exponential is much more complicated. So it's the exponential of sum over connected graphs of the type that I will explain of, well, some contributions of these graphs. So I will draw sort of some typical graph. So I will be drawing the graph on the surface, although it's not actually a ribbon graph, but I just want to emphasize that some vertices are boundary vertices and some vertices are in vertices. Sorry, there are boundary vertices and there are bulk vertices. So there could be some, I don't know, some loops. All edges are oriented. So the boundary vertices are univalent. And I'm also allowed to have sort of loose leaves with one of the two possible orientations. So each such picture becomes an expression which is a polynomial. It's an integral over. Okay, it's a polynomial in the boundary B and A fields, and a polynomial in the zero modes. All right. So it's constructed by certain rules. The contribution of this graph. So the contribution of a graph is, okay, it's h to the negative Euler characteristic of the graph divided by the number of automorphisms, and then the integral over configuration space of points on M, where I have several points traveling on the in boundary, several points traveling on the out boundary, and several bulk points. So my vertices of my graph are decorated by this data, in, out, or bulk. And then I'm integrating some differential form gamma. It's a differential form on the configuration space. And then, well, you construct this differential form as a product of various entities associated with the vertices and edges of the graph. So for a kind of an out vertex, you associate just the A at that point. For an in vertex, you associate B at that point. For an edge, you associate the propagator, eta of xy, where xy are positions of these 2 points, and here I'm integrating over the positions. For my inner vertices, internal vertices, not the bulk vertices, they have several in and several out kind of half edges. And here I just take the appropriate coefficient of the Taylor expansion of theta, where I take the term of like this degree in A coordinate and this degree in B coordinate. So what else? What else? And I also have this sort of zero mode leaves or half edges decorated by either A or B. So yeah, so that's it. So from this constructor, from this assembly kit, you are assembling this differential form. So
Sorry, can you say again what is configuration gamma?
right, so it's actually a configuration of configurations of several points on M. So there will be more precisely M points on the M in points on the in boundary, M out points on the out boundary, and M bulk points in the bulk of M.
And what's the role of gamma?
Gamma is a graph. It's an abstract graph where vertices are decorated as either in vertices, out vertices, or bulk vertices. It's just an abstract piece of data that you decorate the vertices with.
But then you choose some paths somewhere in the definition of gamma.
I choose paths? No, I don't choose paths.
This is just, I see, this is just kind of schematic.
Yes.
Just which pairs to take.
Yes, absolutely. Yeah, yeah. These edges, they are combinatorial. They're combinatorial. Yes, yes. There's a separate story about first quantization picture where you would make them actually paths, but we are not doing that here. So yeah, okay. So you obtain actually some explicit polynomials in the boundary fields and the residual fields. So attached to each graph, and each graph includes in it some explicit computation of a configuration space integral, and these are kind of, so the coefficients of those polynomials are given by configuration space integrals. So these are interesting integrals. They are not easy to evaluate, but they are well defined. So what you produce is sort of a mathematically well defined formula, and for it then you start checking the axioms, and well, let me just tell you that all the axioms hold. And this is an interesting check. And for instance, the check of the, I didn't tell you how to construct omega, but omega is actually itself given in terms of also configuration space integrals, but now you are integrating over configurations of points in a sort of tiny half space, kind of based on a point on the boundary. So the little n-dimensional half space which approximates the behavior of M near the boundary. So you have similar sort of integrals that give you a formula for omega in this case. So omega, as I told you, is complicated. So omega is given by itself by configuration space integrals. So it's ultimately some kind of configurations, and there are some kind of outgoing edges and something attached to the boundary, and that gives you a higher order differential operator in the field. So these outgoing edges give you a differentiation, and this gives you a multiplication by the field on the boundary. And here you have some configuration space integral to evaluate. And it's interesting to, yes, so the quantum master equation comes from Stokes' theorem for integrals over a configuration space. And then you need to study the various boundaries of the compactified configuration space, and this study of the boundary contributions actually gives you the correct formula for omega and gives you this expression for which the quantum master equation holds, and also omega will square to 0, which is also this similar Stokes type argument for configuration space integrals. Finally, I should say that gluing here also works, and it's kind of it works in an interesting way. So that some kind of Feynman diagram on a glued manifold. So you can just see it as arising from two diagrams on M1 and M2, into which this kind of cut is cutting your diagram. So maybe on this, so gluing of partition functions comes in some way from gluing of Feynman diagrams. I'm out of time, and let me stop here. So at least I reached some Feynman diagrams. So let's be happy with that. So thank you.